So for your major north-south roads in the Detroit area, you can take 2,000 times the mile road, add 5,000 to get to your address. So for instance, f of 11 would be 27,000. And when you compare that to Jack's Car Wash, which is just a little bit off the corner of 11 Mile and Woodward, take a look at the address. Where is it? Oh, no, stop, back up. There we go. Just over 27,000, meaning it's just a little bit north of 11 Mile. Pretty cool. So this is kind of a nice little trick. If you don't have your phone available to you and you're trying to decide, is it worth a drive out to some place, you can figure out where it's at. But you've got to kind of do the opposite of the function. The function starts out with a mile road and gives you an address. But what we're going to look for is something that does the opposite. We want to start out with the address and come up with a mile road. That would be useful. So it's the inverse function, something that undoes what the function does. So we're going to have to start out with something like 27,000 and come up with something like 11. Now, to make this a little bit easier and something that I can graph and it'll look pretty nice, let's throw out the units of thousands. Let's just understand that we're working in thousands, and we'll plug in a few values for our function, and then we'll plot them. So I'm going to plot them in orange. So for instance, if we're at 1 mile road, and I think Ford Road in our area would be 0 mile road. So 1 mile road would be, well, 2 times 1 plus 5, you'd be in the 7,000 block. All right, now I'm not sure this trick works all the way down there. That's okay. What about if we were at 3 mile road? So a couple miles further north, maybe Ann Arbor Trail or something like that. Now what would you be?
11.
Yeah, 11. And then one more at 5 mile road. Well, then you'd be at, 15. All right. And those are already plotted for you right here. So 1 and 7, 3 and 11, and 5 and 15. So we can play connect the dots if you want. And I've got rulers that I'll put up here. You don't need to give me an ID to borrow them. So if you want to borrow a ruler, that's great. Let's play connect the dots with these functions, or these points, I should say. And that's our function. But that's the function. What we want to play with is the inverse function. So for instance, in the inverse function, I want to input a 1, I want to input a 7, which is our address in terms of thousands, 7,000s. And what do I want to get out? I want to put in the address and get out the mile road. So I'll input a 7 and output a 1. Or how about this? If I input an 11, what should I output? A 3. And last one, input a 15 and output a 5. Nice. So that's going to be these points right here. And we'll play connect the dots. I'm only going to draw this line down to the x-axis. Like that. So here's your function. We'll call this y equals f of x. And this is your inverse function. Now your inverse function has some notation that, it's a little bit funny. F negative 1 of x. Now, let me be clear about something. This is not a reciprocal. It's in no way related to the reciprocal of this function. It stands for the inverse function. Inverse function. Okay. Now there's a peculiar line in between there, between these two functions, and I want to point out what that is. And maybe we can kind of help ourselves figure it out. Let's see. That's this line right here. Now, the equations of a line typically follow this form, y equals mx plus b. What's the m and b stand for in this kind of situation? That would be 2 and 5 if we were looking at this one. But I'm looking at this one. In general terms, though, what does the M represent? What does the B represent?
M is the slope.
M is the slope, and B is the y-intercept. So let's start out with B for this. What's the y-intercept for this graph? 0, right? Okay. So that just gives us y equals mx. Now we need to figure out what the slope is. But if I go over 5 and up 5, then the ratio of the rise over the run is 5 over 5. So B equals 0. What does M equal? 1. In other words, if I put a 1 in here and a 0 here, I get the equation y equals x. And this is kind of an important line. It's a line of symmetry. And it actually shows you something interesting about these two graphs. They're symmetric across that line. So that's one of the conclusions that I'd like you to have in looking at this handout. So let's kind of back up a little bit, or let me zoom out a little bit here. And one of the conclusions that I want you to have is that the graph of f inverse of x is a reflection around the line y equals x of the graph of f of x. They're mirror images of each other. So you can have one graph, then the other graph. They're reflections of each other. And that's a useful thing to know. In fact, let's practice that a little bit. I'm going to give you a chance to practice that in a second, but I'll give you an example first. Let's flip this over. Take a look at the next page. And what I've got is a bunch of graphs here. I've got 8 of them in total, and they're a bunch of pairs. One graph's the function, one graph's the inverse. So let's start with example A here. And what you have to do is you have to imagine what happens if you flip this around that line y equals x. What graph would you get? Does it look like there's one that seems like it matches, that when you flip it? Which one? C. Yeah. C is the graph of the inverse. Okay? So you got your function, you got your inverse. What I want you to do, and what you can do at home if you're watching this later, is try and find the rest of the function and inverse pairs. So when you're looking at this graph, here's your function. What's its inverse going to look like? And there is a little bit of a trick that you can do if you're a little unsure, if you're trying to decide between a couple graphs. One of the tricks that you can use is this. This graph passes through the point 2, 0. Now when you flip it, and if you look at what we did here, what happened with these coordinates when I went from the function to the inverse? They flipped. So instead of a point at 2 and 0, you're going to have a point at 0 and 2. Yeah, nice. So try and find the inverses for the remaining graphs. And this is all I can zoom out, so. Check with a neighbor. See if you agree. You guys have the same pairs. These worked out okay? Did you get a handout? Okay. So are we in agreement on some of these things? What's the inverse for graph B? Throw out a letter for me, please. H. Yeah, H is the inverse of B. So that one here. Not doing a wonderful job of tracing it. All right, good. What goes with D? Which graph's the inverse of D? E. So let's just take a look at this, and maybe we'll spot check a point here for ourselves. But it looks like we got a point at right here, 1, -1. 1, -1. So that means -1, 1 should be a point on this graph. And looks like we got a winner. So yeah, nice. You could check more points, but this one looks pretty clear. Let me zoom out a little bit and look at graph F. Well, I guess we only got one of these things left, right? The one that I'll point out that we've got here, we've got a point at 1 and 0. So what point should I find in my other graph? What point should be on the graph of G?
0, 1.
Yeah, 0, 1. Nice. Now this graph here happens to be something called an exponential function. We'll study that in chapter 4, along with its inverse, which is a logarithmic function. Nice. Now, are all these inverse graphs functions? So like, for instance, for graph B, we found the inverse was h. Is h a function? No. Ella's shaking her head and like, no. Why not? She's right. Why not? How come this isn't a function?
Vertical line test?
Yeah, it fails the vertical line test. Now that feels kind of like a lot of work. And as much as possible, I'll save you as much work as I can to calculate the inverse and graph it and say, oh, man, it doesn't pass the vertical line test. It's a lot of work. But that vertical line here is equivalent to a horizontal line here. So that gives you a faster way to decide if this has an inverse, which is a function. It has an inverse, but the inverse isn't a function. So the horizontal line test says if you draw a horizontal line through this and it intersects the graph at more than one place, then your graph doesn't have an inverse. So, okay. This one, you can tell right away it fails the horizontal line test because most horizontal lines are going to intersect twice. So this one subsequently fails the vertical line test. But we knew that right here. How about D? Does D pass the horizontal line test? Are horizontal lines going to intersect this graph more than once? No. At most, they'll intersect one time. So if you look over here, that means the graph of its inverse passes the vertical line test. So it's going to be a nice property that we're going to look for, is if something passes the horizontal line test, that means its inverse is going to pass the vertical line test. Now, let's look back at this part right here. What we have to do is we've got to undo this function to find its inverse. So there's some steps here to finding the inverse. First, you're going to replace f of x by y, assuming that your graph or your function is written in f of x form. Replace f of x by y, then interchange x and y, solve for y, and the last step, please don't forget this last step because it's going to cost you a point if you do. That's your inverse notation. I want you to use that to represent the function in the appropriate spots. So let's start out up here. Let's see. We'll do f of x equals 2x plus 5. And then that's going to mean our first step is going to replace f of x by y. So I get 2x plus 5. The second step is to interchange x and y. So let me change things up a little bit this way too. That's going to mean x equals 2y plus 5. Now that interchange step kind of reflects what we did here. To go from the function to the inverse, we swapped coordinates. We interchanged x and y. So we're doing the same kind of thing, just in general terms. Now we want to solve for y. So what do I need to do to solve for y? What would be a first step? Yeah. Yeah, subtract 5.
Would you divide it by 2 so you x minus 5 all over 2?
Yep. X minus 5 over 2. So x minus 5 over 2 equals y. Oops. No. Oh, phew. So it's still step 3. Step 4, thank you, is replace that with f inverse of x equals x minus 5 over 2. Nice. Nice. So that's your inverse function. This is what you can use to try and decide, you know, where something is. If you can just work with the thousands, etc. I first started thinking with this when one of my students found out I was a cyclist and invited me to the family's bike store, Hellybuck Cyclery, which was like on the 61,000 block of Mound Road. And I thought for a second, I'm like, yeah, I live in Royal Oak. There's no way I'm going out to 28 Mile and Mound. It's just a long haul. He was shocked. I didn't pull out my phone and look at Google Maps or something like that. So how can you do that? How can you do that for yourself? Well, if you're at the 61,000 block, let's just throw out the thousands and work with this part right here. What's 61 minus 5? 56. And 56 divided by 2 is 28. So you're at the 28,000 block of Mound. Wow, pretty cool. So it's kind of a nice function. You know, everyone's got phones with maps and stuff like that, so it's not as cool as it used to be, but it does work. All right, how are we looking on the first part here? These first 2 sheets, doing good? Let me reiterate something here. And we're going to do it, you're going to do it through example A. This is the graph of y equals x squared. Does this function have an inverse that is also a function? Yes or no? What do you think? Well, if you were actually to calculate this, and you could do that, you could say, all right, f of x is x squared. So following along our steps from the other page, y equals x squared, or x equals y squared. How would you solve for y here? And be careful, there's a step that people tend to forget. How would you get y by itself? You're going to take the square root on both sides, but there's something we're kind of forgetting here. Yeah, you need the plus or minus there. And it's that plus or minus that gives you each branch of the parabola. So top branch and the bottom branch, plus or minus x. And last but not least, f inverse of x equals plus or minus the square root of x. So for each x, there's two values of y, and that's the problem here. It fails the vertical line test. Of course, we did a lot more work in doing that than we had to because we have the horizontal line test. So here it is a little bit more formally. A function will have an inverse function if it passes the horizontal line test. That is, any horizontal line will touch the graph at most one place. Functions that pass the horizontal line test are special. They're called one-to-one functions. So if it's a one-to-one function, it means it passed the horizontal line test. So if you've got your graphing calculator, you can bust it out for a second, and we'll take a look at a couple examples here. If you don't have one, please borrow one. Just kind of like a quick little foray into some graphing here, some reminders. I'm going to input each function into the y equals, the equation editor. So you press the y equals, we'll put in y equals x to the fourth minus 4x squared, and also y equals x cubed. Now for that second function, you might notice that the equals sign isn't highlighted. That's because I shut it off, because I only want to graph one of these at a time. You can turn them on and off by putting the cursor over the equal sign and pressing enter. So right now I would get both graphs. I don't really want both graphs. I'm just going to shut off the second graph so I graph these one at a time. If you don't know where to graph these things, then just do the standard window, which is zoom 6. So if you type zoom 6, you should get a graph that looks like this. So the quick question to you then is, does this graph pass the horizontal line test?
No.
Ella's got the answer. All right, so we got a no there. Zandos, what do you think?
What's the question again?
Does the function pass the horizontal line test?
Yes.
Yes? Stan, do you agree?
Horizontal?
Horizontal.
Oh, no.
Ah, okay. So a no. Stan, do you still agree?
I agree now.
Okay, he agrees now. All right, good. Thanks, gentlemen. So it fails a horizontal line test. So does this graph have an inverse? Which is a function. No. It's not one-to-one. Not one-to-one. Okay. Thanks, gentlemen. Let's take a look at the next one. For that, I'm going to go back to my equation editor and shut off the first graph, and then cursor below and turn on the second graph, and I'll get the graph of the cubic. Hopefully this is something that you're getting increasingly familiar with. There's the cubic. So what do you think? Leo, does this one pass the horizontal line test?
I think it does.
Yeah. If you're a little bit worried about what happens at 0, we're okay there. It does pass the horizontal line test at 0. So good eye. Appreciate the caution there. It does pass the horizontal line test. So if it passes the horizontal line test, is this a one-to-one function? One-to-one function. Now there's something cool that you can do on Desmos with these graphs. And that is you can get the graph of the function and the inverse pretty easily. So let me open up a new window for Desmos. And I'll graph y equals x cubed. So if I was actually trying to find the inverse function, an expression for that, what would be my next step? I've got y equals x cubed. What's the next step in trying to find the inverse? I mean, you could think, well, all right, usually you start out with f of x, then you replace it with x or y replaces the f of x. But what's the next step after that? Anyone? You look back on your handout, that's fine.
Swap y and x.
Swap y and x. And this is something you just can't do on your graphing calculator, but watch. Let me put in x equals y cubed. And there's your inverse. That's pretty cool. You don't have to have y solved for in decimals. And take a look at this. Let me add in one other line here, y equals x, and let me change it up a little bit. There you go. Do these graphs look symmetric around that line? Absolutely. Absolutely. In fact, there's something else that I didn't point out when we were looking through this. One of the things that happens when you're working or you're going between a function and its inverse is this. Let's look at the domain and range of example A. The domain is all real numbers, right? Does anyone remember the fancy notation they use for that? Script R. Yeah, well done. The range is a little different. Range starts at 0 and goes to infinity. Okay. How about we look at the inverse graph? What's the domain now?
Starting at 0 and going to infinity.
Yeah. So the domain this time starts at 0 and goes to infinity. How about the range? Keeps on going up, keeps on going down. What's the range? All real numbers. So if you want to write negative infinity to infinity, that's fine. I'm going to write r, but keep in mind that that's really negative infinity to infinity, or all real numbers. Can anyone see something that looks kind of like a coincidence? It's probably more than just a coincidence. What happened when you looked at the domain and range between the function and the inverse? So this is f of x, this is f inverse of x.
They switched.
Yeah, they switched, right? All they did was they interchanged. And if you look back at your handout, you'll see exactly that. That when you're looking at the domain of a function, it's going to be the range of the inverse and vice versa. So those two things switch. Nice. All right, so nice little thing to notice. Let's take a look at example C. There's a lot of problems like this in the book, I think, or at least in your homework. I'm in the habit of calling it a book. You've got an e-book nowadays. They're asking you for f inverse of 3 and f inverse of 8. Now let's understand something about the inverse function. Now, right here I called it g of x, but it's really f inverse of x is x minus 5 over 2. I called it g of x just because it's a little bit more friendly notation here. But looking back here and looking here, the idea behind the inverse is that you're inputting the y value and you're outputting the x value. So if you input a value of, say, 3, that's really the y value of your function for f of x. So you're inputting a 3, 1, 2, 3, and that goes along with this value for x, 1, 2, 3, 4, 5. So you would output a 5. So we input a 3 for the y value, you're going to output the x value, which would be a 5. See if you can't do the next one. What if you input an 8? What should you output? Oops, that's a 6. What value am I outputting? What value should I output from this? 8. So it just happens to be a nice little coincidence here that if you input a y value of 8, then your output's going to be an x value of 8. There is another way you can do that. Let's take a look at, see if we can't draw the inverse function. So for instance, it looks like the graph here passes through the point 2, 0. So that means on my graph of the inverse, I should have a point at 0, 2. The graph looks like it passes through just about, I don't know, it's pretty close to -1. It might not be exactly -1. We'll call it 0, -1. That means my graph should be at -1 and 0. About. How about this point? It has coordinates of 5 and 3. Where should my inverse point be? 3, 5. So 3 and 5. It's going to be up here. And I think I've got enough to graph this. Now, interestingly enough, my point at 8 and 8 is going to be the same in both graphs. So that's okay. Let's see if we can't play connect the dots. And there's the graph of our inverse. You could actually use this now to figure this kind of stuff out in a different way. So if you input a 3, you should output a 5 into the inverse graph. Nice. Okay, let's flip it over. Your turn for 1. If the point 2, 5 is on the graph of the function, then what point's on the graph of the inverse? Go ahead. Yeah, 5, 2. Thank you. 5 and 2. And then below that, determine which of these graphs are 1 to 1. Which of these graphs are 1 to 1? Okay. How about the first one? Is this one a 1 to 1 function? How do you tell? First of all, what do you have to do to tell if it's a 1 to 1 function? Yeah, you have to get the horizontal line test. Nolan, what do you think? Is this one a 1 to 1 function?
Yes, I do.
Yeah, it passes the horizontal line test. So it is a horizontal, or it is a 1 to 1 function. Passes, you don't have to write out horizontal line test, just write out HLT. Passes the HLT, so it is 1 to 1. Nice. How about the next one there? Is that next one, Kenzie? What do you think? Is this next one a 1 to 1 function?
No, because it would wrong place.
Yeah, right here, kind of what my son used to call an epic fail. All right, it fails the horizontal line test pretty bad because it intersects the graph an infinite number of points. So it fails the horizontal line test, fails the HLT. So it's not one-to-one. Awesome. And the last one. How about that last one? Is it a one-to-one function? It's a function, passes the vertical line test, but is it a one-to-one function? What we got on that last one?
Yeah.
Got to vote for yeah. All right. Thanks, Jude. Not agreement from Stan, so I think we're looking good. Yeah, it passes the horizontal line test. So yes, passes the horizontal line test. So it's one-to-one. Nice. Okay, so let's back up a second and see if you still remember the stuff we did in example C and D. Assume that f is a one-to-one function. If f of 6 equals 2, find f inverse of 2. So a little thought problem there for yourself real quick. What are we thinking on this one? Millie, what do you think? If you input a 2 into the inverse function, what should I output?
Would it be 6 or?
Yeah. So what's happening here is for the function, you input a 6 and you output a 2. That's the function. That's your x and y. With the inverse, those two things get switched. So if you input a 6, you're going to output a 2. So again, you've got your x and y, but they've been flipped from the graph of the function. So yeah, just kind of flipping that around. Problem number G is kind of a clever example on as kind of a follow-up for F. But are we okay with F? I'm not sure. Did we get a thumbs up from you guys? Yeah. All right. Thank you. Yeah, Mag?
I think the blue is wrong. It should be 2, 6, right?
Yeah. Thank you. Let's see. So no. Let's see.
Was I wrong?
No, I think this one's wrong.
Oh.
No, wait, no, this one's right. Input a 6, output a 2. Yeah, you're right. It should be input a 2, output a 6. So no, thank you so much. Thank you. I'd hate for that to go unnoticed. So there we go. Little Photoshop, and it never happened. Cool. All right. Yeah, we input the y value and you output the x value from the perspective of the function. So let's try that again. This is kind of a good problem. I like it. I don't know if it's going to make the cut for, an exam, but it's a good problem, and it's going back to this kind of thing here. So let's look at f inverse of 0. Now with the inverse function, you're inputting the y from the function, and you're outputting the x. So I'm going to start with the y value. Remember, that's f of x is really taking the place of y. Let's up this way a little bit. So you look around until you find the y value of 0. That's here. What x value goes with that? So f inverse of 0 would be 3. So this becomes f inverse of 3. Okay. Now play that same game again. Try and figure out, well, what's f inverse of 3? What do we got here? F inverse of 3 would be what? 2. Nice. You find the y value of 3. It goes along with the x value of 2 from the function. So overall, the answer here is 2. Nice. Nice. Now, one of the things you can do when you're playing around with functions is check that something's an inverse by applying what's called the inverse property. So we're going to go back to the front of our handout for one last time. And I'm going to highlight this part right here. Before I look at that in detail, let's take a look at this. What if I did a function and then immediately followed up with its inverse? So I did f of x, which gave me 27,000, and then I did f inverse, and I come back to here. And I end up kind of where you started, right? F of 11 gave me 27,000. F inverse would give me back 11. So if you do the function then the inverse, or the inverse then the function, you're going to end up back where you started. And that's what this is saying. It's saying, you know, if you do this, you're going to end up back where you started. And that's what's supposed to happen. What the function does, the inverse is supposed to undo. So if you start out with 28, you do your function, you get 61,000, and you do the inverse function, you get back to 28. So that's what this is saying right here. Let's see that that happens for these kinds of graphs. And we're going to actually check this out a couple different ways. The first one is what's called the inverse function property. And that was highlighted on the other page, inverse function property. And that's this right here. So let's see what happens there. Well, what's supposed to happen is you're supposed to do f of g of x and get x. So let me color these a little bit so you can kind of follow along. Color that one in a hot pink, this one in orange. And I'll start by calculating f of g of x. Well, g of x is really just x minus 9 over 8. So instead of g of x, I'm going to write x minus 9 over 8. And now I'm going to put that into the function for f of x. Now the function for f of x says, well, whatever you put here, you're going to take and multiply it by 8 and then add 9. So that means that whole expression there comes in here. I'm going to multiply by 8 and then add 9. Let's see if that works out pretty good for us. So it's going to be x minus, that's not bright enough. X minus 9 divided by 8 plus 9. Okay. Does anyone see any simplification there? Griffin, what do you think? Is there any simplification on that one?
Did you cancel the 9?
Not quite yet.
No. The 8?
Yeah, we cancel the 8s. So that leaves us with x minus 9 plus 9. Someone want to bust out a graphing calculator for me? Add those two together. All right. You're just left with x, right? Okay. So it worked one way. F of g of x gave me x. Great. Let's see if it works the other way. Let's start out with g of x and then put in f of x. So g of f of x Well, we'll start out by putting in f of x. F of x, just kind of keeping track of these things, highlighted, was 8x plus 9. So we're going to put that into the rule for g of x. Try it yourself. Try putting it into the rule for g of x. What's that going to look like? See if you can't simplify it. In the numerator, the 9's cancel each other out, so I end up with 8x over 8, which is again x. So I get the same thing twice. Either way I calculate this, I ended up with x. So nice. So you can confirm and prove that way that those two functions are inverses of each other. But there's two other approaches that we're going to consider. First things first, are you okay with this? Now, it's not my habit to make you do both of these calculations, but sometimes I might say, well, this happens and this happens. What does that say about the relationship between f of x and g of x? And the response that I'd be looking for would be that they're inverse functions of each other. That's what that information is telling you. Now, how else can we decide, are they inverse functions? Well, we could just calculate it. So let's take a look again. This is example H. You can start out with f of x equals 8x plus 9. And then run through the steps. The first one is replace f of x by y. Oops, sorry, I didn't realize it was off screen. What's the second step? Nick? H?
Flip the x and the y.
Yeah, flip x and y. X equals 8y plus 9. And Nick, what should I do now? You can tell me in general terms or specific, doesn't matter. Other Nick. Nick C? Oh. Maybe some help? Hello? What do I do now? I'm trying to find the inverse. I replace f of x by y, and then I'm interchange x and y. What's the next step? Okay. Good. Subtract 9. And one last step there. What else do we have to do in step 3 here? Yeah, divide both sides by 8. Awesome, thank you. And then the very last step that I want to see if I asked you a problem like this on the exam would be to write it as f inverse of x equals 8 minus, or x minus 9 over 8. And that function matches our g of x. So those two are inverse. So matches g of x. So the functions are inverses. Nice. So that's two ways you can check to see if those two functions are inverses. Let's do one last one. So let me get rid of this and replace this with 8x plus 9. And I can't see the graph, so let me just kind of zoom out a little bit so I can see the, might help if I turn it on. There you go. There's the graph. How about the graph of the inverse? Well, the graph of the inverse is y equals x minus 9 divided by 8. So those two functions look like they're inverses of each other. Yeah, they do. Now, what can happen depending on your settings is if your settings aren't to scale, maybe something like that. Do those look like inverses of each other? Do they look symmetric around the line? No. But that's because I've zoomed in tremendously on the y-axis. So let's go up here to Tools, and there's something called Zoom Square. This will square things up so that way the proportions are what you expect. You can actually add in the line y equals x if you want to, just to be really super careful. And let's make that a dashed line. But now you can see that, yeah, okay, these look like inverses. You could check some points, this. Now you can do the same thing on a graphing calculator. If you don't have decimals to use on a test, then you can do this on a graphing calculator. So same kind of game there. We'll do 8x plus 9. And then x minus 9 divided by 8. I'm going to hit zoom 0, or zoom 6 to get the standard graph, and it just doesn't look quite right. Did I make a mistake here someplace? Oh yeah, I put an 8 cubed there. So there's a couple reasons that it didn't look right, one of which was that I had 512 there in the denominator. That looks pretty good, but if you want to do the same thing that I did just a minute ago, then you can hit zoom square to square things up. And now that's looking a little bit better. You can then add the graph of y equals x if you want to. So there's 3 different ways we looked at it. We looked at the inverse function property, we looked at the graphs, and we actually calculated it. So there's a lot of different approaches that can show you that one function is or is not an inverse of the other one. All right, almost done. We got 2 more to do. I saved the best for last, all right? This kind of a problem is a Math 1150 problem. That's pretty easy to find the inverse of a linear function. Our functions are going to be a little bit more involved here. So we'll take a look at example I. F of x is 1 over x plus 7. All right. Now, as you're working your exams, keep in mind I give partial credit. So the first step would be y equals 1 over x plus 7. What's the second step going to be?
X equals 1 over y plus 7.
Nice. Interchange x and y. X equals 1 over y plus 7. Now, here comes the tough part. You get to solve for y. So that's going to be a little bit more challenging. One of the things about getting y by itself that you might recognize is going to be a problem is that it's in the denominator of this function. So we're going to have to work a little bit harder to get y by itself. Now, anytime that I'm solving an equation and I've got a fraction, multiply, yeah. We're going to multiply by the lowest common denominator. In this case, that's just y plus 7. I'm going to multiply both sides by y plus 7. Let's start out with the easy part. On the right-hand side, I get what? Liv? What's going to happen when I multiply 1 over y plus 7 times y plus 7? What am I going to be left with? Well, the y plus 7 on top and y plus 7 on the bottom would be 1. Nice. So this has to distribute itself to both terms here and here. Now on the left-hand side, I don't get that nice simplification, do I? I just get x times y plus 7. But I at least got that y term out of the denominator. So, okay, now I need to get y by itself. You could, if you wanted, divide both sides by x. That might work for some people. Some people might not see that. Most of you are probably going to be comfortable saying, all right, well, that's xy plus 7x equals 1. And now I want to get y by itself. So there's 2 steps to getting y by itself. What would you do next? What's an easy thing to do to start getting y by itself? You could divide by x. If we were going to divide by x, I would have done it up here. But yeah, you could divide by x. That would work.
Minus 7x.
Minus 7x. All right. Let's subtract 7x from both sides. That gives me xy equals 1 minus 7x. Looking better there. What's the last step then?
Divide by x.
Yeah. Now we'll divide by x and get y equals 1 minus 7x over, excuse me, that should be an x. Nice. Over x. And finally, our fourth and last step is f inverse of x equals 1 minus 7x over x. Now, Kenzie had a good suggestion, divide by x. If you're going to divide by x, I would have done it here. You're going to get something equivalent, but you know it's just a different path to the same equivalent answer. It'll just look a little different, that's all. Let's try example J. Example J is a little harder, but you've got a little clue that you should have picked up on from this graph or from this example. Let's take a look at example J. F of x is x minus 7 over x plus 7. Aurora, get me started, please. What should I do first? Yeah, y equals x minus 7 over x plus 7. Good. Tell you what, keep going. What's the next step? X equals y minus 7 over y plus 7. Nice. Notice she had to change that y in a couple places. That's okay. Let's keep going. Suggestions for our next step. Ethan, what would you do here?
To get the denominator y out of the denominator, you would multiply by y plus 7.
Yeah. So in this case, again, we're going to clear out the denominators by multiplying by y plus 7 on both sides. On the left-hand side, I'm just stuck with, you know, x times y plus 7. What happens on the right-hand side? What's the nice thing that happens there?
Cancels out the denominator.
Yeah, cancels out that denominator. Hasta la vista. So it leaves you with y minus 7. Can you see this one's going to be a little bit trickier than the last one? We've got y on both sides. So, So I guess what I'll do first is I'll distribute and get xy plus 7x equals y minus 7. And now you've got to decide, which side of this equation do you want to put the y on? Do you want to put the y's on the left, or do you want to put the y's on the right? Where are we going to go with those? It's up to you. It doesn't make a difference to me. Just pick one side.
Right.
Pick the right-hand side? All right. Pick the right-hand side. So I want to move that term to the right-hand side and this term to the left-hand side. When something switches sides, what happens to its signs? When I move that 7 to the left-hand side, is it still going to be a negative 7 on the left-hand side? what's it going to be? It's going to be a positive 7. So this is going to be 7 plus 7x equals y minus xy. So switch sides, switch signs. Okay. I still don't have y by itself. So do yourself a little favor. Put a little star by this step in your notes, because this is the second of the tricks here. So when you're reviewing your notes, getting ready for an exam, like, oh yeah, I don't want to forget that trick. To get the y by itself, what I can do on the right-hand side is factor out the y. Y is common to both of those terms. I'm just going to pull it out. If I take out the y from this term, what am I going to leave behind? An x, good, and that x has a negative sign in front of it. If I take out this y, I've got to leave kind of a placeholder behind. What would that placeholder be? A 1. You can check it by distributing y minus xy. On the left-hand side, that's still 7 plus 7x. But I'm almost done. What's the last step there? To solve for y. What do you got to do to get y by itself? Liv?
Can you divide by the 1 minus x?
Yep. We're going to divide both sides by 1 minus x. 1 minus x. And that's going to give me 7 plus 7x over 1 minus x equals y. Nice. Nice. And that is your inverse function. The inverse of x is 7 plus 7x over 1 minus x. Nice. If you're doing this at home, maybe it's part of your homework, and you're like, I want to make sure I got this right because I hate typing this into WebAssign. So what you could do is first of all graph the function y equals x minus 7, and then highlight this, hit the divide key over x plus 7. So that's my function. And then its inverse, one way to get the inverse is just type this, x equals y minus 7 divided by y plus 7. That's the inverse. Let's compare the inverse to what we calculated, which is y equals 7 plus 7x divided by 1 minus x. Now, how will I know if I got this thing right? Well, this graph and what I'm about to type should be the same, right? And guess what? You turn off one, turn on the other, they're exactly the same. So you feel pretty confident that you got this one right. Jude?
Could you go back to example I?
Yeah, sure. Let's go back to example I.
Could you show us how to solve it without distributing to x?
Sure, sure. It was kind of something I was thinking about anyways. So let's go back to here. And we've got x times y plus 7 equals 1. So this is an alternative. If I'm looking at this going, I want to get y by itself, one possibility is just to divide out the x. Kenzie suggested just the same. Now, I guess the reason I was a little bit reluctant to do that is because most people don't see that trick. But if you do divide both sides by x, you end up with, well, y plus 7, because the x's cancel, equals 1 over x. Now, how do you solve for y from here? Yeah, just subtract 7. So y equals 1 over x minus 7. And if you take a look at this, if you split this up, as 1 over x minus 7x over x, that simplifies exactly to what we got, doesn't it? So it's probably a little bit faster if you happen to see this as opposed to what we did. So it's your pick, but now you've seen them both and they both work. So great question. Thanks, Jude. Anything else? All right. That's it for section 2.8.